Welcome everyone to this week's Udacity Deep Reinforcement Learning Nanodegree weekly webinar. This week I'll be going through convolutional networks tutorial in PyTorch. So basically last week I went through PyTorch, an introduction. Now I'm going to go a bit more into convolutional networks. Convolutional networks you'll use quite a lot in deep reinforcement learning. As you know, the deep is used quite a lot with images. And also you could use it with time-based. So first, what I'll cover this week, I'll basically cover why convolutional neural networks, how does a convolutional neural network work. I'll go through feature mapping, polling, polling strides and downsampling, polling padding, why is polling used in convolutional networks, then go on to as it moves on to the fully connected layers. Once I've gone through the basics of convolutional networks, I'll be implementing a convolutional neural network in PyTorch, which go through loading the data set, creating the model, training the model, and testing the model. And then I'll just have a bit of a summary. So, right at the beginning, why convolutional neural networks? So, fully connected neural networks with a few layers can only do a certain amount, and with image classification, it's necessary to go deeper. So, a lot more layers than what you would normally use in a normal problem. But the problem is if you add lots of layers, you get the problem of vanishing gradients, which can be fixed with ReLU. But another issue for deep fully connected networks is that the number of trainable parameters in the model weights can grow quite rapidly. And this basically means that the training slows down or becomes practically impossible, and also exposes the model to overfitting, which is quite bad. Convolutional neural networks try to solve the second problem by exploiting the correlation between adjacent inputs in the images. So, for instance, in a cat and dog, it's looking for the pixels close to the cat's eyes rather than, say, the pixels of the dog on the other side's nose, because that's not relevant to actually picking up features. So basically this means that not every node in the network needs to be connected to every other node in the next layer. And this cuts down the number of weight parameters required to be trained in the model. Convolutional neural networks also have some tricks, other tricks, which improve training, but I'll get into them a little bit in the next section. So, how does a convolutional neural network work? Well, I've got these diagrams on the right here, which is showing basically some pixels. So, first thing to understand in a convolutional neural network is the actual convolution part. So this is basically a fancy mathematical word that is essentially a moving window or filter which goes across the images. The moving window applies to certain neighborhood of nodes as shown in the slide. Here the filter applied is 0.5xx the node value. Only two outputs have been shown in the diagram above, where each output node is a map from the 2x2 input square. The weight of the mapping of each input square, as previously mentioned, is 0.5 across all four inputs. So the outputs can be calculated, as you can see. How does convolutional networks work? Well, in the convolutional part of the neural network, we can imagine this 2x2 moving filter sliding across all available nodes, pixels in the input image. This operation can be illustrated using a standard neural network node diagram. The first position of the moving filter connection is illustrated by a blue connection, and the second is shown by green lines. The weights of each of these connections is stated previously is 0.5. There are a few things in a convolutional step which improves training by reducing parameter weights. Sparse connections, so not every node in the first input layer is connected to every node in the second layer. This is contrary to fully connected neural networks, where every node is connected to every other in the following layer. Constant filter parameter, So each filter has a constant parameters. In other words, as the filter moves around the image, the same weights are applied to each 2 times 2 set of nodes. Each filter as such can be trained to perform certain specific transformation of the input space. Therefore, each filter has a certain set of weights that are applied for each convolution operation. This reduces the number of parameters. Note, this is not to say that each weight is constant within the filter. In example previously, the weights were 0.5, 0.5, 0.5, 0.5, but could have just easily been something like 0.25, 0.1, 0.8, 0.001. It all depends on each filter is trained. These two properties of convolutional neural networks can drastically reduce the number of parameters which need to be trained. So the next step in a convolutional neural network structure is to pass the output of the convolution operation through a non-linear activation function, generally some version of ReLU activation function. This provides a standard non-linear behavior that neural networks are known for. The process involved is this convolution block, often called feature mapping. This refers to the idea of each convolution filter can be trained to search for different features in the image, which can be used in classification. Before we move on to the next main feature of convolutional neural networks, called pooling, we'll examine the idea feature mapping and channels in the next section. Feature mapping and multiple channels. So, as mentioned previously, because the weights of the individual filters are held constant as they are applied over the input node, they can be trained to select certain features from the input data. In the case of images, it learns to recognize common geometrical objects such as lines, edges, and other shapes which make up objects. This is where the name feature mapping comes from. Because of this, any convolutional layer needs multiple filters which are trained to detect different features. So therefore, the previous moving filter diagram needs to be updated to look something like this. Feature mapping and multiple channels, part 2. Well, now you can see on the right-hand side of the diagram that there are multiple stacked outputs from the convolution operation. This is because there are multiple trained filters which produce their own 2D output for 2D images. These multiple filters are commonly called channels in deep learning. Each of these channels will end up being trained to detect certain key features in the image. The output of the convolution layer for a grayscale image like MNIST dataset will therefore actually have a 3 dimensions, 2D for each of the channels, then another dimension for the number of different channels. In the input itself, multiple channeled, as the case of color RGB images, 1 channel for RGB, the output will be actually 4D. Thankfully, any deep learning library worth its salt, PyTorch included, will be able to handle all mapping easily for you. Finally, don't forget that the output of the convolution operation will be passed through an activation for each node. So now the next vitally important part of the convolutional network concept is called pooling. Pooling. So now you can see there are 2 main benefits of pooling in convolutional neural networks. These are, it reduces the number of parameters in a model by a process called downsampling. So what is pooling? It also makes detection more robust object recognition and scale changes. So what is pooling? It's another sliding window type technique, but instead of applying weights, each can be trained. It applies a statistical function, some type of content on its window. The most common type of pooling is called max pooling, which you may have heard of, and it applies as the max function over the content of the window. There are other variants, mean pooling, which takes a statistical mean of the contents, which are also used in some cases. In this tutorial, we'll be concentrating on max pooling. The diagram to the side shows an example of max pooling operation, as you can see, and then that's the max from that, that's the max from that, and it's sliding across, bang, bang. The basics of pooling. In the diagram above, you can observe the max pooling taking effect. For first window in blue, you can see that the max pooling outputs 3, which is the maximum node value for that 2x2 window. Likewise, the green 2x2 is output of 5.0 and the maximum of 7.1 for the red. In the pooling diagram to the side, you will notice that the pooling window shifts to the right each time by 2 places. This is called a stride. In the diagram, stride is only shown in the X direction, but the goal was to prevent pooling window overlap. The stride would also have to be 2 in the Y direction, so otherwise 2 by 2. Another important thing to notice, you see, is pooling is the greater the stride, the greater then the output size will be reduced, as you can see, because it will be, so if it's only doing a little one or if it's doing a massive jump, but also you don't want to be leaving sections. As can be observed above, the 5x5 input is reduced to a 3x3 input. This is a good thing. It's called downsampling and reduces the number of trainable parameters. So now it's only training off that rather than all of these. Another thing to notice in pooling diagram above is that the extra columns. So these are called padding. So this makes the effective size of the pooling space equal to 6x6. So this is to ensure that the 2x type pooling window can operate correctly with a stride of 2.2, and it's called padding. Basically, they're just dummy things to fill up the space, so the the maths works, and it can slide across 2x2x2, which is 6. Padding will need to be considered when constructing our convolutional neural network too. So now that you have an understanding of this, what else does it do? Why is max pooling used so frequently? So in addition to the function of downsampling, pooling is used in a convolutional network to make detections in certain features somewhat invariant to scale and orientation changes. Another way of thinking about that pooling does is that it generalizes over lower levels more complex information. Let's imagine the case where we have a convolutional filter that during training learns to detect the digit 9 in various orientations with the input images. In order for the convolutional neural network to classify the appearance of 9 in the images correctly, it needs in some way to activate whenever a 9 is found somewhere in the image, no matter what the size of the orientation the digit is, except for when it looks like 6, that is. Pooling can assist with a higher level generalized feature selection, as the diagram to the side shows. Why is pooling used in convolutional networks part 2? Well, the diagram is a stylized representation of pooling operation. If we consider that the small region input image has a digit 9 in it, green box, and assume we are trying to detect such digit in the image, what will happen is that if we have a few convolutional filters, they will learn to activate via the reload. When they see a 9 in the image, return a large output. However, they will activate more or less strongly depending on what orientation a 9 is. We want the network to detect 9 in the image regardless of what the orientation is, and this is where the pooling comes in. It looks over the output of these 3 filters and gives a high output so long as any one of the filters has a high activation. Therefore, pooling acts as a generalizer to lower the level data, and so is a way of enabling the network to move more high resolution data to low resolution information. In other words, pooling coupled with convolutional filter attempts to detect objects within an image. The final picture. So, the image to the side, which really shows the structure of fully developed convolutional network. If you work the image above from left to right, we see that there is a robot, then scanning over the images as a series of convolutional filters or feature mapping. The output of these filters is then subsampled by pooling operation. And after this, there is another set of convolutions and pooling on the output for the first convolution pooling operation. Finally, the output there is attached a fully connected layer. The purpose of this fully connected layer at the output of the neural network requires some explanation, which I'll go into further. So the fully connected layer. As previously discussed, a convolutional neural network takes high resolution data, effectively resolves that into a representation of objects. Fully connected layer can therefore be thought as attaching a standard classifier into the information-rich output of the network to interpret the results of finally produced classification. Almost like a hierarchical sort of way of learning outputs. In order to attach this fully connected layer to the network, the dimensions of the output of the convolutional neural network need to be flattened. So consider the previous diagram. As the output, we have multiple channels of X, X, Y matrices, tensors. Then channels need to be flattened. Consider an example. Let's say we have 100 channels of 2 by 2 matrices representing the output of the final cornering operation of the network. Therefore, this needs to be flattened to 2 times 2 times 100 equals 400 rows. This can be easily performed by PyTorch and will be demonstrated below. Now, the basics of the convolutional neural network has been covered. It's time to show you how it can be implemented in PyTorch. So, implementing convolutional neural networks in PyTorch. So, here is the input. So, any deep learning framework worth its salt can be able to handle convolutional neural network operations. PyTorch is such a framework, and in this section, I'll show you how to create convolutional neural networks in PyTorch, going step by step. Ideally, you already have some notion of the basics of PyTorch, otherwise you're welcome to wing it. The network we're going to build will perform an endless digit classification. Convolutional neural network architecture that we're going to build can be seen in the diagram on the side. So, first up, we see that the input image is a 28 by 28 pixel grayscale representation of digits. The first layer will consist of 32 channels of a 5 by 5 convolution filter plus a relay activation, followed by a 2 by 2 max polling downsampling with a stride of 2. This gives a 14 by 14 output. In the next layer, we have a 14 by 4 output of layer 1 being scanned again with a 64 channels of 5 by 5 convolutional filters and a final 2 by 2 max poll stride 2 downsampling to produce a 7 by 7 output of a layer 2. After the convolutional part of the network, there will be a flatten operation which creates a 7 by 7 times 64, so basically 3,164 nodes, an intermediate layer of 5,000 fully connected nodes, and a softmax operation over 10 output nodes to produce class probabilities. These layers represent the output classifier. So first we're going to load the data set. So PyTorch has an integrated endless data set in the Torch Vision package we can use via the data loader functionality. In the subsection, I'll go through how to set up the data loader for endless data set. First, some preliminary variables need to be defined. First up, we need to set up some training hyperparameters. So 5 epochs, number of classes 10, batch size 100, learning rate 0.001. So as you can see, and then we've got the data path to the folders for endless data set, and we will basically the model store path. Next, we set up the transfer to apply the endless data set and also data set variables. So as you can see, the first thing we note is the transform.compose function. This function comes from the top Torch Vision package. It allows the developer to set up various manipulations on the specified data. So numerous transforms can be chained together in a list using a compose function. In this case, we specify the transform will convert the input dataset into a PyTorch tensor. PyTorch tensor is a specific data type used in PyTorch after all, and various data and weight operations within the network. In its essence, though, it's simply a multi-dimensional matrix. In any case, PyTorch requires a data set to be transformed into a tensor, so it can be consumed by the training and testing of the network. The first thing we note above in the previous diagram is the transform compose. This function comes from the convolutional package. I have doubled up my slide. I'll move on to the next one. Sorry, the next argument in the composed list is a normalized transformation. So basically what it's doing is normalizing the data. So neural networks tend to work better if you normalize data between -1 to 2 and 0 to 1. So -1 to 1, and 0 to 1. So to do this in PyTorch, normalized transform, we need to supply a mean and standard deviation of the MNIST dataset, which in this case is 0.1307 and 0.3081 respectively. Note, for each input channel, a mean and standard deviation must be supplied. In MNIST's case, the input data is only a single channel, but for something like the Sci-Fi dataset, which has 3 channels, 1 for each color in the RGB spectrum, you will need to provide a mean standard deviation for the channel. Next, train the dataset and test the dataset objects need to be created. These subsequently be passed by the data loader in order to create these datasets from the MNIST dataset. First, the root argument specified for the folder where is train.pt and test.pt data files exist. The train argument is a boolean, which informs the dataset to pick up the train.p data file and the test.pt data file. The next argument, transform, is where we supply any transform objects that we've created to apply the dataset. And finally, the download argument tells the MNIST dataset functionality to download the data, if required, from an online source, as you can see. Okay, so basically here, train loader equals data loader. It's got the data set, which is train data set, and the batch size, which we had in the things. Shuffling it, missing a little bit of stuff. Oh, there it is. The test loader equals the same thing, test data set, batch size, shuffle. It's not false. So now we can train the test data set and have created. It's time to load them into the data loader. So the data loader object in PyTorch provides a number of features which are useful in consuming training data. The ability to shuffle the data easily, and ability to easily batch the data, and finally to make data consumption more efficient via the ability to load the data in parallel using multiprocessing. It can be observed there are 3 simple arguments to supply. First, the data set you wish to load. Second, the batch size you desire. And finally, whether you visit or randomly shuffle the data. Data loader can be used as an iterators so that you extract the data can be just use the standard Python iterators such as enumerate. This will be shown to practice later in the tutorial. So let's create the model. So we basically created the model. So set up our NN model class, which will define the convolutional neural network which you're going to train. So this is an overview. So I'll go through it step by step. So this is where the model definition takes place. The most straightforward way to create a neural network structure in PyTorch is using the NN model. The NN model is very useful in PyTorch class, which contains all you need to construct a typical deep neural network. It also has a handy function, such as a way to move variables and operations into a GPU back to CPU. Apply recursive functions across all properties in the class by resetting all the weight variables, creating streamlined interface for training, and so on. It's worth checking out all the methods at the links. At the PyTorch docs. The first step to create is a sequential layer object within the class. So we've created sequential layer. First, we create a layer self.layer1 by creating an n sequential object. This method allows us to create sequential ordered layers in our network, as described in the previous webinar. And a handy way of creating a convolution plus reload plus pooling sequence. And it can be observed the first element in the sequence definition is a conv2d.nn method. As you can see, convolutional 2D, reload, and max pooling. And then we have a basically, so As you can see, the first argument is the number of input channels. In this case, it's our single channel ray eminence image, so the argument is 1. The second argument to the Conv2D is the number of output channels, as shown in the model architecture diagram. The first convolutional filter layer comprises of 32 channels, and then it's got the kernel size and stuff, which I'll go into a bit. The kernel size is the argument, is the size of convolutional filter. In this case, we want a 5 by 5 size convolutional filter. So there it is, kernel size 5, which would be 5 by 5. A stride is so it only moves one across at a time. We put padding to try to even it up a bit. If you want to filter which different size end shapes, the X and Y directions, you supply a tuple, X size, Y size. Finally, we need to specify the padding argument. This takes a little more thought. The output size of any dimension from either the convolutional filtering or pooling operation can be calculated by following the equation. So F is the filter size, P is the padding, and S is the stride. The same formula applies in the height calculation. Seeing as our image and filters are symmetric, the same formula applies to both. If we wish to keep an input and output dimension the same, with the filter size 5 and stride of 1, it turns out from the above formula that we need a padding of 2. Therefore, the argument for padding is convolute is 2. See? The next element in the sequence is a reload, so activation. So the last element that is added to the sequential definition for the self-labor is the max pooling, as you can see, with a kernel size of 2 and a stride of 2. So the first argument in the pooling size, which is 2 times 2, and hence the argument is 2. Second, we want to downsample a data by reducing the effective image size by a factor of 2. To do this, using the formula, we set the stride to 2 and the padding to 0. Therefore, the stride argument is equal to 2. The padding argument default 0. We don't specify it, so that's what is done in the code above. For these calculations, we know that the output from self.layer1 will be 32 channels of 14 by 14 images. Next, the second layer, self.layer2, is defined in the same way as the first layer. The only difference is that the input from the convolutional function is now 32 channels with an output. So it's basically taking 32 and an output of 64 channels. So using the same logic, and given that the pooling downsampling, the output from the self.layer is 64 channels of 7 by 7 images. Next, we specify a dropout layer to avoid overfitting. And finally, the two fully connected layers are created. And the first layer will be a 7 times 7 times 64 node, and will be connected to the second layer of 1000 nodes. To create a fully connected layer in PyTorch, we need the NN linear method. The first argument to this method is the number of nodes in the layer, and the second argument then is the number of nodes in the following layer. And then it's the output of 10, as you can see. So we also need to create a forward function method. So with the init definition, the layer definition have now been created. The next step is to define how the data flows through these layers. It's important to call the function forward, as it will override the base forward function in the NN model and allow all the NN model functionality to work correctly. As can be observed, it takes the input argument X, which is the data that is to be passed through the model, i.e. a batch of data. We pass this batch into the first layer, self.layer, and return the output as out. This output is then fed into the following layer, and so on. Note, after self.layer2, we apply a reshape function to out, which flattens the data dimension from a 7 by 7 64 into a 3,164 times 1. Next, the dropout is applied, followed by the 2 fully connected layers, and the final output being returned from the function. Now let's train it. So we call it. So before we can train the model, we have to first create an instance of our class. First instance, conv.net is created calling model. You may notice that we haven't yet defined the softmax activation for the final classification layer. This is because the cross-entry loss function combines both softmax activation and cross-entry loss function in the same function. Winning. Next, we define the atom optimizer. The first argument passed to the function are the parameters we want to optimize training. This is made easy by the NN model class, which CovNet derives from. All we have to do is pass model.parameters with the function, and PyTorch keeps track of all the parameters within the model which are required to be trained. Finally, the learning rate is applied. So we've basically got the criterion, and then we have put through the whole parameters and the learning rate for the optimizer. So next, the most important part to start with are 2 loops. The first, the number of epochs and to loop over, and within it, and we'll interact over the train loader using enumerate. Within the inner loop, first the output of the forward pass through the model are calculated by passing images, which is a batch of normalized endless images from train loader. Note, we don't have to call model.forward images, as the NN model knows that forward needs to be called, and when it executes model images, .training loop is created. The next step is to pass the model output and then true images labels to the cross-entry loss function defined in the criterion. The loss is appended to the list, and it will be used later to plot the progress of the training. The next step is to perform backpropagation as an optimized training step. First, the gradient has to be zeroed, which can be easily done using zero.grad. Next, we call basically backwards of the loss variable to perform a backpropagation. By now, the gradients have been calculated in the backpropagation, we simply call optimize step to perform an atom optimized training step. PyTorch makes training the model very easy and intuitive. The next set of steps involves keeping track of the accuracy. Prediction of the model can be determined by using the torch.max function, which returns the index of maximum values in the texture. The first argument to the function intends to be examined, and the second argument is the axis over which is to determine the index of maximum. The output tensor from the model will be the size of batch 10. To determine the model prediction for each sample in the batch, we need to find the maximum value over 10 output nodes. Each of these will correspond to one of the handwritten digits, output to be correspond to 2. The output node with the highest value will be the prediction of the model. Therefore, we need a set of second arguments of the torch max function to 1. This points the max function to examine the output node axis and axis 0 corresponding to the batch size dimensions. This returns a list of predictions, integers for the model, and the next line compares the prediction, predicted equals labels, and sums them to determine how much correct predictions they are. Note the output of sum is still a tensor, so to access its value, you need to call item. We divide the number to correct predictions by batch size equivalent, the label size to obtain accuracy. Finally, during training, after 100 iterations of the inner loop, the progress is printed. Ta-da! And this is basically what we get as it prints it out. To test the model, we use the following code. So we just use eval, testing it out, tells us how many we get total, and we print that out. So as you can see, the first step, we set the model and we do model.val. This is a handy function which disables any dropouts or batch normalization layers in your model, which will befuddle your model evaluation testing. The torch.ngrad statement disables the auto-grad functionality in the model. As it's not needed in model testing evaluation, this will act to speed up computation. The rest is the same accuracy calculation during training, except that in this case the code iterates to the test loader. Finally, the result of output is to the console, and is then saved. So we print it and then we save it. And the last part of the model is performance and plotting. So basically, as you can see, the test accuracy of the model after 10,000 test images is 99.3, and it can be observed that it was quite rapidly achieves high degree of accuracy on training set, and test set accuracy after 6 epochs arrives at 99%. Not bad, certainly better than the accuracy achieved in a basic fully connected neural network. So the summary is, in this tutorial, you've learned all about the benefits of structures of convolutional neural networks and how they work. You've also learned how to implement them in awesome PyTorch deep learning frameworks, a framework which, in my view, has a big future, and I hope it's useful. Have fun in deep learning journey. Now we can have a bit of a Q&A. I guess no one's got any questions. Wait for a little bit more. All good. Well, thank you very much for this webinar, and I hope this week's really good. There'll be some really interesting projects that are coming through from students, and unbelievable what you guys are achieving. So yeah, like I said, reach out to me at any time, and if you need a meeting, book it in and have a chat. All right, thank you very much for this evening. Goodbye.